This podcast is a continuation in our series on the kinetic molecular theory and gases. This one deals with Graham's law of effusion. Now, effusion is defined as the passage of a gas through a small hole into an evacuated space. And the rate of effusion measures how fast this thing happens. Graham's law of effusion states that the rate is inversely proportional to the square root of the mass of the particles, and it's something that he determined back in the 19th century. Mathematically, it's expressed as follows. The rate of effusion for gas 1 relative to the rate of effusion for gas 2 is equal to the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. And as you can see down below, you have the gas on one side, a pinhole, and a vacuum. And the rate of gas getting through that hole is what we measure. It can be derived from the kinetic molecular theory, which is testament to the validity of the theory. The effusion rate is, after all, related to the speeds. And the speeds are equal to, the root mean square speed, 3RT over the molar mass. And if you put the equation together and do the algebra, you get Graham's law. And so once again, the experimental results affirm kinetic molecular theory. The spreading of gas through a room is called diffusion. Now, diffusion is actually quite slow, considering that molecules are moving at hundreds of meters a second. But it all goes down to that mean free path thing and the fact that there are collisions with other molecules, molecules of oxygen, nitrogen, carbon dioxide, and other things in the air, for example. That slows down the rate of effusion, but we can still come up with our best estimate of the rate of diffusion by looking at Graham's law of effusion. But they're not the same thing. Sample problem. Helium effuses through a porous cylinder 13.2 times faster than an unknown. What's the molar mass of the unknown? Well, you have Graham's law, you put the values in, and you see that the square root of molar mass 2 is on top. Solving, we get 352 grams per mole. So if you had some other information about the compound, you could probably figure out what it was. What you do, need to know, is that we're talking about rates, not about times. And students get tripped up by this. If it took 6.5 minutes for a liter of argon to effuse through a porous barrier, how long will it take for a liter of chlorine? So the rate will be comparing the same amount of gas, but you need to put the rates in, which is 1 over 6.5 minutes, 1 liter divided by 6.5 minutes, 1 liter divided by the time for chlorine, is the ratio of the square roots of the molar masses. And this way we come up with 8.66 minutes for chlorine, which should make sense since it's about twice as heavy and the square root is, well, you know. And so this is a good use of Graham's law of effusion. Our final podcast in this series will look at real gases.